Hello everyone. So in this pre-lecture tutorial, we're going to build on what we learned related to the structure of molecules and polyatomic ions by recalling what we've done with Lewis structures, but then also on top of that, building on top of that knowledge with some new theoretical content. Because up to this point, basically, we've learned how to represent molecules and polyatomic ions in two dimensions. So basically flat on a piece of paper or on the electronic workspace on Mastering Chemistry, but molecules aren't just flat. They exist in three dimensions. And so we have to understand how these molecules actually exist in three dimensions if we're going to understand their behavior and their function properly as correlated to their structure. And the way to do that is to incorporate a theory that we're going to learn about in the next section of Chapter 10. And this theory is often called VSEPR theory. Basically, the abbreviation is VSEPR. And basically what it stands for is valence shell electron pair repulsion. And I know that sounds kind of fancy, but in general, the idea behind it is actually quite simple. It builds off of the fundamental scientific idea that basically things that have similar charges repel each other. So since electrons all have negative charges, basically they will repel each other. Now, this is true of electrons that are basically traveling through space within an atom, but it's also true of electrons that exist in structures of molecules. So whether these electrons are involved in bonds or whether they're lone pairs located on atoms within a structure, basically electrons will still repel each other. That does not change simply because they're part of a molecular structure as opposed to an atomic structure. And so these repulsions are what cause molecules to actually take on the specific shapes that they do. And so, in general, we have to find a way to refer to these shapes and also to be able to predict what shape a molecule will take based on the situation of what we will call electron domains. And electron domains, what I mean by that very simply is, again, a space that electrons occupy within a Lewis structure. So basically, electron domains can be either bonds of all varieties, single bonds or multiple bonds, and they can also be lone pairs as well. Okay, so when we actually have a structure in front of us, then it's somewhat easier to visualize what these molecular structures are going to look like. So on these next few slides, I've actually included pictures from a simulation that we'll also be using in class to sort of help ourselves out in terms of understanding this stuff. But suppose here that this purple atom represents a central atom within a Lewis structure. And notice that this central atom contains a single bond to this white atom on the right, and it also contains another single bond to the white atom on the left. And so basically, I have two single bonds around this central atom. Each of these single bonds can be considered an electron domain. And so basically, this particular model molecule has two electron domains. Okay? Now, if we consider the tendency of electrons to repel each other, that means that the electrons in each bond will want to get as far away from each other as possible. And when these electrostatic repulsions occur, the furthest that they can get from each other and still remain connected to the central atom would be if they are 180 degrees apart from each other. And so as a result, basically that causes any molecule that has a central atom with two electron domains, it'll cause that particular molecule to have a linear, what we call electron domain geometry, and also a linear molecular geometry. So basically that means that this molecule has all of its atoms in a straight line. Okay? But what would happen if I had three domains instead? Well, basically, here's one possibility. Notice that here's our central atom again. And this central atom has 1, 2, 3 single bonds. And these 3 single bonds, each of the single bonds is what we would refer to as an electron domain. And so that means that this particular model molecule has 3 electron domains. Okay? Now, the farthest apart that these 3 electron domains can be from each other and still remain connected to that central atom, that would actually be achieved if each of these electron domains are 120 degrees apart from each other. And so when I have a molecule with 3 electron domains like this, then basically what I'm going to get is an electron geometry or electron domain geometry that we refer to as trigonal planar. Okay, notice that the geometry of the molecule would also be considered to be trigonal planar. What it means to be trigonal planar, trigonal means 3-sided, and planar just means flat. So basically I have something that's flat and 3-sided, because if you can imagine, if I connect the white atoms to each other, basically I get a 3-sided figure, a triangle. And so as a result, I refer to this geometry as trigonal planar. But remember I said earlier that basically electron domains can be bonds or they can be lone pairs as well. And so what if I have a model molecule that has 1 lone pair, but 2 bonds? Okay, well, basically that would still be considered 3 electron domains, because electron domains can be bonds or they can be lone pairs. And so, once again, basically the bond angle that would encourage the most separation between the electron pairs would be a 120 degree angle between the domains. But when we refer to the geometry of the molecule only depends on the actual presence of atoms at the ends of bonds. So basically it's this shape from the white atom to the central purple atom to the other white atom that's bonded on the other side that describes the molecular geometry. Even though the electron geometry is still trigonal planar because of the 3 electron domains, we don't refer to the geometry of this particular molecule as trigonal planar because I don't have an atom bonded at this site. Basically, that's still a lone pair. And so if I just follow what the molecule looks like based on where atoms are located and not lone pairs, then basically I see that the shape looks just sort of like a bent line. And so for that reason, even though the electron domain geometry is trigonal planar, the molecular geometry is considered to be bent because it looks like a bent line. All right. Now, what happens when I have 4 electron domains? When I have 4 electron domains, then let's take the case where I have 4 single bonds. Okay, so basically here I can no longer keep the electron pairs involved in these domains in 2 dimensions. Basically, if you notice, if I had 2 electron domains, basically I had a straight line. If I had 3 electron domains, basically I still had a shape that was flat or somewhat 2-dimensional, and I was able to achieve maximum separation between the electron pairs. If I try and do that when I have 4 domains, then basically I would have to go and, if I'm going to keep it flat, I'd have to use a 90-degree angle between the electron domains. But I can actually do better in terms of this angle of separation if the molecule actually exists in 3 dimensions and not just 2. Because in 3 dimensions, basically I can get a bond angle that's 109.5 degrees instead. And so when I have that type of arrangement where I have 4 single bonds, and again 4 electron domains, then basically I have this shape that's now more 3-dimensional. It sort of looks like a pyramid with an antenna sort of sticking out of the top. And essentially what I get if I connect the sides together, and it's sort of hard to see even in this picture alone, what I get is sort of a four-sided figure in 3 dimensions. And that type of figure is called a tetrahedron. All right, tetra means 4. And again, this suffix means a three-sided shape. I'm sorry, a three-dimensional shape. And so because of that, then I call this electron domain geometry tetrahedral. Notice that because there are no lone pairs on the central atom, then the molecular geometry and the electron domain geometry are considered the same. But what if we do have a lone pair? Or if we have a lone pair there, then basically, again, the electron domain geometry would still be considered tetrahedral because I still have 4 electron domains. But now, because of this lone pair, remember that the molecular geometry is actually determined by the presence of the atoms, not the lone pairs. And so if I connect the atoms to each other, it's kind of hard to see, but it sort of looks like just a pyramid, a three-sided pyramid. Basically, there's this side, and then the side that's behind the plane of the molecule that we're looking at. So basically, the atoms and bonds form a three-sided pyramid. And so that's why we call this particular molecular geometry trigonal pyramidal. All right, pyramidal for pyramid, then trigonal for three-sided. Okay, now there still is one other option to consider, because what if I had 2 lone pairs in my 4 electron domains? And so here, since again I'm still working with 4 electron domains, then that's considered tetrahedral electron domain geometry for the 4 electron domains. But if you notice what the atoms and bonds are doing by themselves, if I connect this atom to the central atom to the white atom that's sticking out towards me, basically it just looks like a bent line. So once again, that molecular geometry would be considered to be bent. Okay, so let's actually take a couple of examples of trying to actually figure out the VSEPR geometries for a few compounds. So let's start with water. All right, now we've been through the process by which you can actually draw the Lewis structure of water, so I'm not going to go through the process from start to finish again. I'll just leave it to you to verify that these structures are correct. But basically, the Lewis structure of water should look like this. All right, basically I have 2 lone pairs, and I have 2 bonds. And so I have 4 electron domains. So the electron domain geometry should be tetrahedral. Right? If I have 4 electron domain geometries, then I should have tetrahedral electron domain geometry. Now, if I have 2 lone pairs within that tetrahedral arrangement, then basically what that means is that it's the shape of the atoms doing their thing that will actually determine the molecular geometry. And the molecular geometry looks just like a bent line. And so as a result, the molecular geometry for the water molecule is bent. What about if I had methane? All right, again, I'll leave it to you to verify that this Lewis structure is correct. But basically, I get this when I draw the Lewis structure of methane. I have 4 single bonds. And these 4 single bonds represent 4 electron domains. And so when I have 4 electron domains, then the electron domain geometry is tetrahedral, and the molecular geometry is also tetrahedral. So basically it would be this case that we covered at the beginning of the prior slide. Okay. One more example. What about ammonia? Well, the Lewis structure of ammonia looks like that. Okay, so basically I have 3 bonds and 1 lone pair. Okay, so basically here I have 4 electron domains. And so as a result, the electron domain geometry would still be considered to be tetrahedral. And the molecular geometry, since I have 1 lone pair, I'm just going to look at what the atoms and bonds are doing. So basically, I'm looking at just this shape. All right, so if I go and I consider what that looks like, doesn't that look like our 3-sided pyramid from this case right here? All right, and if it does, and it does, then basically what I have is a 3-sided or a trigonal pyramid. So our molecular geometry would be trigonal pyramidal for this case. All right, so this is a skill that's going to require a little bit of practice. It requires a little bit of imagination and also a little bit of sort of experience trying to sort of work these problems. And so go ahead and work on the follow-up assignment. We'll continue to reinforce this concept in class next week. So if you have any questions, by all means email or bring up your questions in class. All right, have a good night.